So hello everyone. I'm Anmol Zehrah. I'm an AI engineer at Atomic Computing, and I basically work as an AI engineer. I have over 2 years of industry experience, and I've had the privilege of doing multiple sessions with TFUG and overall as well. So before we without further delays, let's just start with the topic. So today I will be discussing about, one of the most important foundations behind modern AI, which is the vector embeddings. And we all are very familiar with using AI systems like, ChatGPT, semantic searching, recommendation engines, RAG-based assistants, all of these different things that we're using. They are all relying on one core idea, which is converting meaning into numbers, right? Like a computer does not naturally understand a word like, car or contract or password, any of these words. So for a computer, these are just text symbols. So AI basically needs a mathematical way to represent meaning, to be able to decode what that set of letters actually mean. So that is exactly what embeddings do. They convert words, sentences, documents, images, products, concepts, all of these into vectors, which is basically a list of numbers. And once the meaning becomes numbers, AI can compare meaning mathematically, and it can understand that car and automobile are similar. Or let's suppose if some query goes like, how do I reset my password? Or I forgot my login credentials. These are semantically the same. So in this session, we will go from basic math of vectors to, practical applications like semantic searching, recommendation systems, LLMs, and as well as RAGs. So let's start with the very basic problem. Computers, they do not understand the way humans do, right? So whenever we see the words like king or queen, we immediately know and we understand that these words are related. And we know that they belong to royalty, right? We also know that king and banana are not closely related. Like, this is what we know from our own human understanding. But when we talk about computers, words are not just symbols, unless we are able to represent them in a numeric form. So, an embedding will be that numerical representation that gives some meaning to it. Like, for example, the word king might have a vector or a numerical representation like this. And queen might become, another vector representing, the word queen. And these two words have similar meaning, right? They are contextually similar. So that's why their vectors will be nearby. They will be close together. So the key idea here is that, words or concepts with similar meanings, they get placed close together in a mathematical space. Okay, and before, embeddings, there is always this one common way to represent words. Like, before we get into this concept of how embeddings work, there was a very basic representation, which was one hot encoding. And let's suppose we have a vocabulary of 5 words, right? And in those 5 words, like, let's suppose I have apple, banana, king, queen, and car. Okay. So now, given that I have 5 different words, if I do one hot encoding, then every word will have its own position and it will only have one in its own slot, right? So this just tells us the identity of the word, but does not tells us the meaning. So one hot encoding was basically used for, identifying a specific word, but it wouldn't really represent it or give any meaning or context to it. But when we talk about dense embeddings, they basically solve this problem. So instead of, just mostly having zeros, we use compact, numerical vectors where patterns basically represent meaning. So king and queen, may have vectors that are very close, but king and, let's suppose, banana, right, might have very different vectors, right? So the most important difference is that, one hot encoding just tells us what the word is, but embeddings are basically what gives us, or, tell us how the word relates to other words, right? Okay, now what is a vector? So let's define, the basic mathematical object here, which is the vector. So, if I want to just simply explain a vector, like, think of vector as an ordered list of numbers. So for example, if I have a simple vector 2 comma 3, it is a 2D vector, a two-dimensional vector, right? Where x plane has just a simple value 2 and the y plane has a simple value 3. But if I talk about the second vector where I have 4 different, data points, that is a 4-dimensional vector, right? So in mathematics, a vector can represent, direction, position, magnitude, multiple things. But when you talk about AI, a vector represents different features, right? So let's suppose if we take an example, like, imagine we represent a movie using multiple features. So, there could be an action movie, a comedy movie, a romantic movie. So these different genres would have different, uh, you know, different mathematical representations. So a movie vector could look like, 0 0.9, 0 0.1, 0 0.2 as a way of representing these different genres. So that just means that movie, like if let's suppose a movie vector is like in the given example, then that can just mean that this movie is strongly action based because it has the highest value for action. So, and has very little of comedy and romance, right? So in real embedding models, humans do not manually define these features, and the model, it basically learns them, automatically. This is exactly why, embeddings are so powerful, because they create hidden feature representations that basically help in, capturing meaning from data. Okay, so a vector space is a mathematical space where all these vectors are present. So in a 2D space, a vector can be shown on a graph, right? So like I said, 2 on the x-axis, 3 on the y-axis. And let's suppose if we have a 3D space, then that point becomes, like that representation will be in 3 different dimensions. But when we talk about AI, embeddings are often living in much higher dimensional spaces, right? So a text embedding might have like, 384 dimensions or 1536 dimensions or even more dimensions, right? So an embedding space is a vector space, where each point is representing meaning. So for example, we have the word cat. It has a point in the space. There is a word dog, which will be another point in the vector space. The word car will also have, a data point in that vector space. Similarly, if there is, you know, a representation for the word vehicle, then car and vehicle will be nearby because they are semantically close. They are, related to each other. Okay. Now, if we talk about dimension, so dimension is like, one numerical axis. Let's suppose when we say 2 dimension, that means, there are 2 numerical axes. So the number of dimensions is basically how many number of axes exist in a vector space. So, like, like I mentioned that when we talk about actual embeddings, they have hundreds and thousands of dimensions. And why is there like, a need for such complex number of dimensions. That is because, human meaning is very complicated, right? Like when we're talking about human language being represented, because, a sentence carries so much information, like, about the topic, about the context, the relationship between different words, the entity types, the domain, the intent of the conversation, the formality. So there are like so many things involved when we talk about, like, a simple sentence of the human language. And let's suppose the word bank, right? Now, in two different sentences, that word bank has different meaning. It completely changes the context, right? So if somebody says that I deposited the money in the bank, that means bank is the financial institution here. While if we have another sentence that says that, he sat on the river bank, here we're talking about the side of a river. So, same word, same spelling, but the context completely changes the meaning here, which is why it is very important, to have these high dimensional embeddings, which allow, AI to be able to represent many subtle details and understand them at the same time. And, like as humans, like, we are very comfortable in visualizing two or three dimensions. But AI systems, like I mentioned, are, working in hundreds and thousands of dimensions. And that high dimensional space is what, allows the model to separate complex meanings. Like, for example, words like doctor, medicine, patient, hospital, all of these words, they, naturally form one region in the embedding space, right? And words like, football, coach, player, stadium, they may form like, another region. So we can imagine that the, embedding space is like, a giant map of meaning. And on this map, related concepts will be close together and unrelated concepts are going to be far apart. So AI is not really understanding the meaning exactly like humans do, but, it's able to capture those similarity patterns, in a very well manner. And this is basically the foundation behind many AI applications. If we now come towards what actually an embedding is, so embedding is just, a learned numerical representation of any data. So, the input that we have could be a word or a sentence, or maybe an image, or a code snippet, or a paragraph, or it could be like any piece of text. And the embedding model will convert that specific input into a vector. Like, for example, if I have a sentence like, how do I reset my password? Now, an embedding model is going to convert this whole sentence, the set of words, into a numerical representation, which will be used for different purposes, right? And the vector, this specific vector, is capturing the meaning of this whole sentence, right? And the most important point being is that embeddings are being learned. They're not manually designed by humans, they're being learned by the model. So, the model will learn from the data and, it will discover or, find out a pattern from that data, right? And once we turn something into a vector, we can compare it mathematically with other vectors. That is exactly why, embeddings are used in searching, in rags, in clustering, in classification problems, in recommendations. So like there are so many different applications where embeddings are being used. Okay, so word embeddings give each word its own vector. So if I have like, a set of words which are similar, like cat and dog, they have similar vectors because, they appear in similar contexts and they share meaning. Similarly, when we talk about car, vehicle, they would be close by, or words like, happy, joyful, they would be close by. So, like for example, there's a very famous example that, king would be king minus man plus woman would give me queen, right? That means that embeddings can capture, relationships as directions in a vector space. And, like the direction from man to woman may be similar to the direction from king to queen, right? And the direction, uh, like this direction is basically, a way that shows that embeddings do not just simply, memorize words, but they're also, able to capture relationship between different words. And this is exactly why, embeddings, they became like, a breakthrough for NLP, natural language processing. Then if we talk about like sentence embeddings, then like, we know that words are very useful, but a lot of times the meaning that we have depends on the full sentence. Like, you cannot understand the meaning of a word just by itself, but you need the context, you need the sentence, or the words around it to make more sense out of it. So if like we look into these two sentences, like, can I return this product, and what is your refund policies? Now these use different words, but the intent is very similar. And a sentence embedding that we have, okay, it basically represents the whole sentence as one word, like, sorry, as one vector. So both of these sentences, they should be able to produce vectors that are very close or similar. So if you look at the vectors given here, you can say that they're very close by, very similar in value, very nearby. And this entire concept is extremely useful in, chatbots and FAQ matching and, intent detection, RAG based systems, semantic searching. All of these use cases, they often depend on sentence embeddings. And, the main idea here is that sentence embeddings are not comparing, like they're not just looking for exact words, but they're actually looking to compare the intent. That is why, this is much better than just simple keyword matching. Now we move on to a concept of concept embeddings, which basically means that, embeddings can actually represent much more than just word and sentences, and they can actually represent, abstract concepts. Like, for example, concepts like, customer satisfaction, purchase intent, legal liability, fraud risk, medical urgency, all of these things can also be represented in a, in an embedding space. Like, let's suppose a customer, sends a message that says, I was charged twice and nobody is helping me. Now, this message is going to, connect multiple concepts together, like, the billing issue, a negative sentiment being there, urgent support, being required, and, a refund request being there in place. So this is like a very powerful use case, if you look in the applications. But it also, this entire concept, it also allows AI systems to, understand, hidden meaning behind different documents, user behavior, messages, product interactions. And this is also why, embeddings are very useful, not only for language understanding, but also for, for personalization, for clustering, for risk detection, all of these different use cases. Then we have geometric meaning. So, once the text has become into vector, the meaning, becomes geometry. This means that now everything that we calculate will be mathematically, right? So we can measure the distance, the similarity, the direction, the angle, the clusters, and even the nearest neighbors, right? So for example, laptop and computer will be very close together in the embedding space, while laptop and, banana will be far apart. Similarly, like refund request and return policy will also be closer together, right? And this basically allows, AI systems to answer a lot of important questions, like, which document best matches this user query, or, which product is closest to users interest, or which support ticket is similar to let's suppose, a previous ticket, or which knowledge chunks, can be sent to a certain LLM. So embeddings is what allow AI to, compare meaning using mathematics behind it. Now let's look at one of the most important operations, in vector math, which is the dot product, right? So if we have two vectors, A and B, the dot product is, calculated by multiplying corresponding values and, adding their result, right? So for example, if I have a vector A 1, 2, 3, and I have a vector B 4, 5, 6, so we just do 1 times 4 is 4, and then 2 times 5 is 10, 3 times 6 is 18, and then we add them together to get like the final output, right? So that equals to 32. So a larger dot product usually means that the vectors are more aligned. And dot product is used almost everywhere in AI, like in neural networks, attention mechanism, recommendation system, similarity searching, everywhere. And in LLM specifically, attention mechanism itself uses dot product to decide which tokens, should pay more attention to which other tokens. Now, magnitude basically means the length of a vector. So for, let's suppose, vector A, the magnitude is calculated using square root of the sum of squared values. Like for example, if I have a vector 3 by 4, I'm simply going to, calculate the magnitude by square root of 3 squared plus 4 squared, right? So that means 9 plus 16, which is 25. And if I take the root, it gives me 5, right? So, but why does, magnitude matter? Because, dot product is very much affected by vector length. A very long vector can produce a very large dot product, right? Even if its direction is not actually meaningful. And that is why we often use cosine similarity, because cosine similarity, it focuses more on direction than on the length, right? So magnitude basically helps us understand the difference between vector length and vector direction. And if we come to cosine similarity, it is basically one of the most important concepts that we have in semantic searching and in like RAGs, because it measures the angle between two vectors. So, we have a very simple formula that the dot product of, two vectors A and B being divided by the magnitude of, A times the magnitude of B. And this result, usually ranges between -1 and 1. And like, a score that is closer to 1 means very similar. If it is around 0, then it means, it's neutral, it's not really related. And if it's -1, that means it's like in the opposite direction, it's not similar. So, for example, if I have words like reset password or forgot credentials, they will have a very high cosine similarity. And let's suppose if we have reset password with best pizza recipe, they will be very far apart. So their similarity is going to be, very negative. So, the reason like cosine similarity is so useful is like, because it focuses on direction and not length. So it basically just helps us in comparing meaning more reliably. Now, this is a very quick worked example to see how cosine similarity can actually be calculated. Now, it's basically distance versus similarity, where we have two complementary ways to compare embeddings, right? So distance basically asks that how far apart the two vectors are. So it's like, a very common, very common distance metrics have like, Euclidean distance, Manhattan distance, etc. So when we have small distance, they're very similar. If there is a large distance, then they're far apart or they're different, right? While if we talk about similarity, in similarity, we basically look into how aligned the two vectors are, right? So common similarity metrics would be like, cosine similarity or the dot product, which basically means that, you know, if there is a high similarity, if the output is high, then they're very similar. If the output is low, then they're very different, right? So in text embeddings, basically, cosine similarity is very popular because it measures the angle, between different meanings. And in recommendation systems, dot product is also very common because, it can capture the preference strength, right? And other than that, both the approaches, they're very useful. So the choice depends on the use case. Then we have the nearest neighbors, right? So nearest neighbors are the closest vectors to any given query in the vector space, right? So let's suppose if a user asks that, how do I change my password? So the system, converts this query into an embedding. Then, it basically searches the stored embeddings and find the most closest ones, right? So for the query that how do I change my password, the similar ones would be reset your password, forget login details, account recovery steps, This is how the semantic search basically works, right? So instead of like matching exact keywords, the system finds, meaning-based matches. So nearest neighbor search is used in like search engines, chatbots, RAG-based systems, image similarity, fraud detection, duplication, recommendations, a lot of different things. And when we talk about at scale, we have millions or billions of vectors. So scanning them, one on one would be like way too slow. And that is exactly why, vector databases, they use optimized, nearest neighbor searching. Then we have vector databases. So, a vector database is what actually stores the embeddings and, it allows fast, similarity search. So if basically, it usually stores, the original text chunk, the vector, the metadata, the source document, the ID, the filters, this is how it should look like, right? So, a vector database is like a search engine, but for meaning, right? So in RAG systems, vector databases, they play a very critical role because they retrieve the most relevant knowledge before the question actually reaches the LLM, right? So the LLM can answer based on relevant information rather than just going into, blind guessing. Now, how are embeddings actually created? So, they're created by the neural networks, right? So let's suppose you provide an input. The model is going to output a dense vector. And during the training, the model would have learned patterns from very large amount of data. And it basically learns which words appear in similar context and, which sentences have similar meanings. So automatically, it is able to calculate which documents will answer similar questions. So, the training objective here is usually to place similar items close together and different items, far apart. So at the beginning, the model does not know meaning, but through training, it gradually organizes the vector space. And, that organization is basically what makes, embeddings so important. Contextual embeddings. Now, we have one same word which has multiple contexts, and every context has a different meaning. So when we talk about the older embeddings, they were very static. That meant that every word had one fixed vector. For example, the word bank had one vector, whether it meant the financial bank, or a river bank, right? And this itself was like a very big limitation. But when we talk about modern embeddings, they are very, very contextual, right? So they generate meaning based on the surrounding words and, so like in the sentence that money in a bank, the model will understand that bank here is the financial institution, right? And let's suppose if the sentence has like the word river bank, the model will know that we're talking about bank as the site of the river. So, it is very important for LLMs, right? Because a word does not have just a meaning, but it depends on the context, right? So modern, the transformer based models that we have, they are very good in capturing this context in a very, strong way. Now let's connect embeddings to LLMs, right? So before an LLM can actually process any kind of text, it converts the text into tokens, right? And then each token is converted into a vector. And this is exactly what we call a token embedding. So let's suppose if I have a word, like a word, let's suppose refund, right? Refund, the token of this will turn into a vector, which may be represented like this, right? And if we just talk about like the token meaning, it is not enough because the model also needs to know the position, right? The order. And knowing that word order is also very important. Like, let's suppose if I have a sentence that the dog chased the cat, and another sentence that says the cat chased the dog, right? Now it has exactly the same words, but they mean very different things. They're basically opposite sentences, right? This is exactly why LLMs, they use position embeddings or positional information, right? So inside the model, almost everything that we have becomes a vector operation, right? So when we talk about an LLM, we're basically, really just sending text that gets transformed into vector and is, being processed in a very, very mathematical intensive calculation. Okay, now attention is, like one of the most key ideas behind transformers and the modern LLM architecture, right? So attention is what helps the model decide which words or tokens matter to each other. So, for example, the animal did not cross the street because it was tired. Now, what does the word it here represents to, right? Most likely it refers to the animal, right? But attention is what helps the model connect these related words. So, mathematically, attention uses vectors, which are called like query key value, which the model compares the query and key vectors using dot product, right? So a higher dot product means there is a stronger attention. So like in simple words, the model is asking that, which words should the way, basically which words should this specific word pay more attention, right? So this is like one of the reasons like why modern LLMs can understand context, using long text. So semantic search. So when we talk about semantic search, that just means that, searching by meaning instead of just, exact keywords. And this process is very simple. Like, first we convert documents into embeddings. Then we store those embeddings in a vector database. Then, we convert the user query into an embedding. Then we compare the query vector with the document vectors. And lastly, we just return the most similar results, right? So this is what makes the search way more smarter. Like for example, a keyword search may fail, when the exact words do not match, right? But in semantic search, it understands that different wording may still mean the same thing. And this is one of the most practical and, most popular use cases of embedding. Now, this is a very quick example. Like, the user asked, how can I get my money back? Right? So a traditional keyword search, might just go and look for words like money and back. But relevant documents, might use words like maybe refund, reimbursement, charge reversal, policy. So, a keyword system will miss those results, while, an embedding search is going to understand the meaning, right? So it will find documents like, refunds are processed in like 7 days, or request reimbursement in the portal, or returns are accepted within 30 days. So this is why, embeddings are extremely useful in customer support, or like, in enterprise level knowledge bases, and like, document searching, because they are matching meaning, not just words. Okay, so when we talk about recommendation systems, so embeddings are also widely used in recommendation systems, right? So both user and items, they can be represented, like, they are represented as vectors. Like, for example, a user vector may represent their preferences, right? A movie vector may represent maybe the movie style, tone, genre, content. So if the user vector is close to the movie vector, then the system may recommend that movie. And that very same idea, it works across videos and products, courses and songs and articles and search queries, and all of this. So, recommendation systems are basically just matching users and items, in the embedding space, right? So basically, an embedding is just helping us in capturing, like, the taste and the preference and everything in a very mathematical form. Now, coming to the RAG systems, RAG is basically retrieval augmented generation. It combines retrieval with the LLM generation. So, instead of just asking an LLM to answer from its own memory, we first retrieve relevant information from like a knowledge base. And in this, basically, embeddings are very critical in this whole process, right? Because the workflow is like, first you split the entire documents into, into chunks. Then you create embeddings for each chunk. Then, store those embeddings into a vector database. Then you embed the user query. Then you retrieve, the top k most similar chunks. Then you send those chunks and the question to the LLM. LLM is, then basically in the process of generating, a grounded answer. And, this is one of the biggest real world use cases of embeddings that we see today, right? So it allows many companies to, connect LLMs with their own documents, policies, PDFs, databases, and all of that. So a very quick RAG example, that let's suppose if a company policy says that, refunds are available within 30 days, or a refund request must include the order ID, or, approved refunds are processed in 7 business days. Now, if the user asks that, how long do I have to request a refund? So the embedding is going to search, the embedding search will basically retrieve the most relevant sentence, right? And then the LLM is going to use that retrieve context to, develop an answer. So without RAG, the LLM might just guess and, might just hallucinate, right? So with RAG, the answer is grounded in, actual contextual company data. And that is what makes RAG so valuable. Okay, if we look into chunking and embedding, right? So chunking is like one of the most important design choices that we have for RAGs. So, documents are often too large to embed as one piece. So, we normally just chunk them, or we just split them into, smaller pieces. But chunking, should be done very carefully. Because if the chunk is too small, you might lose context. If it is, it will be incomplete. And that's why, a good chunk is something that is, the right sized and is semantically complete, has the complete semantics intact, right? And this is basically very easy for LLMs to use. Okay, then there is also another concept, which is top K retrieval. So top K retrieval just means that, you return the most similar results here. So when you say top K is equals to 3, that means it will return the 3 most closest chunk to the query, right?
And choosing the k is very important, because if your k value is too small, then the system may not capture all the important context. If it's too large, then the LLM may start to get irrelevant information, the cost might be more, and your answer may not be as relevant. And a lot of different rack systems, they use between 3 and 10 as their top k value, depending on the use case, because the top k is like basically you need to strike a balance here between relevance and completeness. If we talk about similarity threshold, it's basically the minimum score that is required to accept a retrieved result. So like when you have like a specific threshold, it basically allows when a chunk is going to be accepted or not accepted, right? So this basically improves the answer relevance and reduces the hallucination risk. Then when we talk about like the quality of an embedding, then a good embedding places similar meanings closer together, and very different meanings far apart. And but when we talk about the quality, it is dependent on multiple factors, like for example training data, your model architecture, the number of dimensions, the relevance of the domain, preprocessing, chunking, similarity metric being used, the retrieval tuning, all of these things. So, a general embedding model may work very well for everyday language, but let's suppose if you have a more specific use case, like maybe legal, medical, financial, technical documents, then you would actually, prefer going for a domain specific embedding model, right? So, like for example, a medical model would better understand relationship between like blood pressure, hypertension, cardiovascular risk, and all of that than a regular generic model. So the best embedding model is not always the most famous one, but the one that is best aligning with your own use case. Now, if you want to visualize an embedding, you cannot actually see when you have hundreds of dimensions, right? We cannot see a 768 dimensional space. So we can reduce it to like 2D or 3D, right? And then we have like dimensionality reduction techniques like PCA and others. And, we use like, basically document embeddings, they appear as clusters, and 2D plotting are done for approximation. So it's like not a full dimensional, high dimensional reality, but it's just, like an overview to understand the visuals better. Embedding in classification. So when we're talking about embeddings, they're also very useful in classification, right? So if you have like a lot of messy data, you convert it into an embedding, then you feed it into a classifier. So like let's suppose if a support ticket is there, it can be classified into categories like billing, technical issue, account access, refund, complaint, and all of these different categories will are different. Like the wording will be different, but like a model will be using embeddings which will classify whether the meaning and the context is similar, right? That is the power of embeddings, that they act as smart numerical features for this messy textual data. Then clustering in embeddings basically just means grouping similar items together without having any predefined labels, right? So, like we can basically take thousands of customer support tickets and convert them into embeddings, and then, cluster them for common issues, right? And this becomes very useful when we do not already know the categories, right? So the data will organize itself based on meaning. So, in these scenarios, embeddings, they really help turn, unstructured data into understandable, groups. Now, embeddings in LLM applications, they basically are the hidden engine behind a lot of different applications that we use today. So, they're highly used with, in chat with documents, in semantic searching, in question answering, in support bots, in knowledge assistance, in contract analysis, resume matching, code searching, personalized recommendations. All of these things, they heavily rely in this embedding processing. So if we look at the mathematical intuition, so let's quickly summarize the core math that we have. So a vector is a list of numbers, and a vector space is where the vectors are actually living, while a dimension is that one feature axis, right? Magnitude, we just looked at that, it's a vector length, and we also saw how we calculate magnitude. We looked into dot product, which measures the alignment. Then we looked into cosine similarity, which calculates, angle-based similarity. And then we also looked into the nearest neighbor, which was closest in terms of meaning. So, the big idea is that embeddings, they basically make meaning measurable, right? So once meaning becomes a vector, we can ask how similar are two ideas, which document is closest to a certain question, and which product matches best to a certain user, which sentence has the same intent. This is how math becomes so useful behind these powerful AI systems that we have today. So just a quick end-to-end example that for example, somebody just says that I forgot my password, how can I get back in? So now the step one would be to convert this query into an embedding, then search the vector database, then retrieve the closest knowledge chunks, then send the question and that retrieved chunk to the LLM, and then the LLM basically generates a very grounded answer and a very relevant answer. So if we talk about the key takeaways that we have here, so just to wrap up the session, we know that AI needs numbers to process language, and embeddings are what actually turn text, data, or images, users, product, concepts, all of this into vectors. And vectors are living in very high dimensional spaces, and whenever we have similar meanings, they will be closer together. Whenever there's a difference in meanings, they will be far apart. And we also saw that dot product is for alignment, cosine is for angle similarity, and vector databases is what enables fast similarity searching. And embeddings are basically what power semantic searching, recommendations, LLMs, the RAG systems. So the most important idea is that embedding turn meaning into math, and AI represents meanings as geometry. So then it uses math to compare and retrieve similar ideas, right? So one big picture is that if we want to explain that, if we want to explain this whole session in one simple picture, then just imagine that every word, every sentence, every document is one point on a giant invisible map, right? And on this map, words like cat and dog, car and vehicle, refund and return policy, password reset, and forgot login are going to be very closer together. So AI does not understand meaning exactly like we do, but it learns where things belong on this very huge map, right? So the points are the vectors, and the map is like this a whole huge embedding space that we have. And the distance or angle between points represents different similarities. That is the big picture behind embeddings. So that just brings me to the conclusion of this session. So thank you, everyone.
If anyone has any questions, feel free to unmute and ask. You can also type your question in the chat.
I have a question. First of all, thank you so much, Anmol, for this amazing session. Anmol, if despite using PCA and these kind of dimensional reduction algorithms, embedding dimensions are increasing. So, what kind of mathematical challenges could arise, and how modern models is addressing it? These kind of curse of dimensionality.
Sorry, could you please repeat your question? I got a bit disconnected in between.
Okay, so I'm asking like as embedding dimension increases despite using the PCA and all these kind of dimensional reduction algorithms, what kind of mathematical challenges could arise like curse of dimensionality, and how we can actually improve them in the modern models, how they are addressing it. I'm audible? I'm audible?
Yes, you are. But Anmol, you are not audible. No, Anmol, you are still not audible. Let's just wait for 2 to 3 minutes. Our speaker is joining in a bit.
Am I audible now?
Yeah, you are audible.
Apologies for for the inconvenience. Okay, so you just asked that for modern AI systems, like when we have things like, when we do PCA or we reduce the dimensionality and we use other techniques, what are the challenges that we face, like, the curse of dimensionality and all of that, right?
Yeah, मतलब embedding की dimensions की space अगर increase हो जाती है तो how we are dealing with them.
Okay, so basically, what happens is that, when you talk about curse of dimensionality, it's basically a cluster of related problems that, that just show up when you're adding a lot of different features and dimensions, because real world use cases have multiple different, dimensions and are not as simple as, simple vector mathematics, right?
Yeah.
And like, the core issue is that volume will exponentially grow with dimension, so your data, becomes very sparse. And like, when we talk about, very high dimensional spaces, the ratio between the nearest and the farthest neighbor tends towards like 1. So the nearest neighbor concept, becomes almost meaningless. So it's like a very, like, look at it as that, when we have embeddings that are normally between like 700 to, thousands of dimensions, the entire point being that, let's suppose the embeddings that are normally routinely working fine with such huge number of dimensions, they basically use a concept called manifold hypothesis, right, where you have real data which does not just fill an ambient space uniformly, but it actually concentrates on, like, a much lower dimensional manifold. And the dimensionality is here far lower than, any other dimensionality. Reason being that, the neural networks that we have, they basically learn that representations that are basically, most aligned to that manifold. So the effective sparsity is, much better than the raw dimensional count that is being applied otherwise, right? So if we talk about like the practical mitigations or what is being done for it, so we normally use like PCA and SVD for, very linear structured or fast processing, data. But if you go for, like, furthermore, for even more in-depth problems, then, we look at furthermore techniques like autoencoders, when you want, a learned non-linear reduction that is basically, fitting into your pipeline. Or sometimes when feature selection is more important than extraction, where interpretability matters more, then you go for regularization techniques like, L1 or lasso regression regularization, right? And then there are sometimes, regularization or inductive bias are the answer, by using like maybe dropouts or weight decay, or, different architectural, priors like maybe attention mechanism or convolution and everything. So specifically for, any vector search context, you need to look into the use case and, decide which kind of, functionality will suit the best. So that's like a, a very practical lever for any kind of use case, depending on the index size and what you're actually looking at.
Okay, means it also depends on the use cases, and according to the use cases, there are different techniques with respect to the use case. I also mentioned. Okay, I have another question that if we want to build our own embedding model, like for Punjabi language, what would be the steps? Like, what kind of foundational knowledge is required to build this kind of system? Audible?
Yes, you are.
Yeah.
So, and the other step would be like, let's suppose you already have like, we already have a lot of these multilingual embedding models, which may
Anmol,
be
I think
able
you were
to,
not audible earlier. Could you please repeat it? The
uh,
answer of the question. Yeah.
was it not audible?
Yeah.
Okay. So basically, when you talk about like for Punjabi language, then
Yeah.
it's going to be very different from how we have English because, we have a lot of dialects and we have a lot of different contextual understanding, right? So,
Hmm.
like, one approach could be that you use an existing multilingual embedding model. Like, there are already a few embedding models which use or like, which already cover Punjabi, but I'm not sure which specific dialects or which specific region do they cater to because I think language itself differs in different regions of the South Asian um, area. So, or you could another approach could be like fine tuning a multilingual base. So this could be like a sweet spot for like maybe a low resource work, like take a strong multilingual embedding model and then maybe fine tune it contrastively on Punjabi
No, actually,
wordings.
actually, I want to understand how to build our own embedding model from the very scratch. I want to understand the foundational level of it, that how this is working. Like, for example, if I take a totally new language, how we have to deal with it. Like, we need some kind of a data set on how we need to incorporate it from the whole series of steps to build on embedding model.
Like you want to build a whole embedding model from
Yeah,
scratch.
yeah. Like, is there any way possible? I just want to actually understand it at how things are working under the hood.
Okay, so like basically if you want to build your own embedding model from scratch, like from the very first step,
Yeah,
so you just want to understand that what are the steps to it, right?
yeah.
Okay, so basically, first of all, you would definitely need data, like, right? Because any kind of embedding model will start from data. So you basically collect all the data, make your own corpus, right? Once you have your corpus ready, like with all the right words that you need, you then build your own tokenizer where it's going to basically, like, like, okay, let's suppose I have, just to give you an example, I take a
Yeah.
language and I have like 500 words of it. Just to give you an example, this could be like billions and millions of words.
Hmm.
Now, after having that data, you basically look into the data quality, you do quality filtering, you basically pre-process your data, bring it in a form that it's ready. The data is ready, then you go for the tokenizer. Now, in the tokenizer, you will basically be, training your own tokenizer model, which will be basically on your own corpus, where you basically decide that which words and sequences are more important. How will your whole embedding table look like? Then you check for how many tokens you want per word. So you decide that, right? So that you
Okay, so
can
I need to
basically,
build an again tokenizer model too.
you'll have to definitely like maybe use unigram or use
Okay, okay.
word
Yes.
piece. You'll have to basically
Yeah.
use tokenizer, otherwise how are you going to have the
Okay,
tokenization done, right?
got it.
And after that, you would actually have to design your architecture, that let's suppose you want just encoder only embedding model, or do you want like a BERT style transformer, or what exactly, how do you want your architecture to look like, right? Because that is the entire, like your entire design choice is going to change how your embedding model looks like. So maybe you decide if you want positional encoding, or if you want what the context length should be and all of that, right? Then you start with the pre-training,
All right.
and then then after that you, and when you're talking about embedding models, it's also important to have like contrastive learning being done, right? This is like, this would be also a very important and a crucial step that you'll have to look into. And then you'll have to build an evaluation, and that needs to be there before, like it needs to be built before you train, because how are you going to track whether or not your model is working a certain way or not, right?
Yeah.
So these are a lot of different things that you need to look into when you're talking about building an embedding model from scratch.
All right, all right. Contrastive learning means I have to do like you give the example of the cat and dog. So we need to compare the cat and a dog that how they are far apart from each other and are close to each other, right? Is it
Yeah, you like that could be a smaller example of it, but like when we say contrastive learning, that is basically, like, let's suppose it is that how you decide that, let's suppose one specific set of tokens, how are they going to pool, like, basically how are they going to be related or differentiable with each other.
okay? They cross relation with each other
Yeah.
in both ways.
Yeah.
With the similarity and the differential. Okay,
Yes.
so and in multimodal, if we're talking about the multimodal data, where we have the imagery data and also some kind of textual data. So when we are dealing with these kind of multimodals, we are saving our embeddings on a different spaces, or we incorporated them in same spaces, same dimensions. How we are dealing with them? Actually, while you are talking to me, I just getting more and more questions. I'm so sorry about that. This is coming with the flow. I'm audible.
Yes, you are. Anmol, you are not audible right now.
Am I
Yes, you are.
okay, Mama? Can you repeat your question?
Okay, I'm asking that if we are talking, if you are working with the multimodal data, where we have the imagery data and the textual data, both kind of data. So we are saving our embedding in different spaces or in the same spaces. How are dealing with the dimensions because they're
That
different kind of the data.
Yeah, that completely depends on the use case and how your architecture looks like, right? So it because if you're talking about building your own model from scratch, your own embedding model from scratch, then that would obviously, depend on how the architecture looks like.
Okay. Okay, it means it depends on the use cases. Right.
Exactly.
Okay. Thank you, Anmol.
All right.
Anmol, there's a question of Harsh. His question is, if AI learns hidden features automatically, how can two completely different objects end up having very similar vector representations?
Okay. So if objects are different, then they wouldn't be similar, right? Like, could there be a bit elaboration here? Like, what do you mean by different objects having similar, like, if they're different, like, are they semantically similar or are they just completely different? Because if they're completely different, then they would not have similar vector representation. Like, a bit of context in this question.
Harsh, if you are here, you can drop your message in the chat or you can just unmute yourself.
Okay, so we're basically saying that different objects, for example, a movie and a song, or a cat and a tiger, and end up having very similar vector representation. What does it indicate about how AI understands and represents meaning? Explain your answer with respect to feature learning, semantic similarity, and vector embeddings. Okay, so when we're talking about words like cat and tiger, now cat and tiger having similar vectors is not really a puzzle here because the system would work correctly, right? Like for example, this share features, both of them are animals, both of them have like similar bodily features, like would have four legs, would have predatory behavior, like in the context when you explain how a tiger looks like and how a cat looks like, they will be very similar in terms of the real features that they share, right? So there, when their vectors are landing in similar context or are closer together, that means that there is a genuine abstraction there, right? Without a specific definition for it. While if you talk about a movie and a song, that is basically because here they are like the different object is like there are different types of media types, even though they're different, but they fall in a similar category, right? Like it wouldn't say anything about their semantically being closed, but both of them are in the similar niche. Song and a movie, they fall in media category, right? Or maybe in the entertainment category, so they're closer together in that context. So when we talk about semantic matching, or how different vectors are closer together, so it depends on the overall context as well. So this is how basically these AI meanings, or these different vectors are closer or far apart in the vector space.